So today we're going to talk about the last part of our concurrency section, and we're going to be describing the HalfSync HalfAsync pattern and explaining how this gets applied in Android. So what we're going to start out by doing first, and you'll see I've changed the format of my slides a little bit as I think about how I'm going to film these things eventually for the Coursera class. I'm trying to keep each of the modules down to about 20 minutes, and this stuff was starting to get about an hour long, so I split it up into a couple parts. So we're first going to start off by talking about what the HalfSync HalfAsync pattern is. And then we're going to talk about how you would implement it and apply it in the context of Android. I will also, as we discuss the pattern, I'll use Android as the running example to motivate this, but a lot of what I'll talk about is not specific to Android, which of course is the entire point of patterns. We use them to help see the generality in design solutions, and the fact that we're going to learn how they apply in Android is kind of icing on the cake, but what's important are the general concepts. So here's the context for this discussion. So you often have concurrent systems that have to perform both synchronous and asynchronous communication, and these things have to communicate with each other somehow. So a good example of this, and you're got a little taste of it now, and we're going to do more of it as we move along, is this kind of threaded download activity, or this threaded download application that we're working on. So you've got some parts of the code that are going to be interacting with the user via the activity part, via the widgets and so on, and some other part that's going to do some downloading. So you have two different parts of the code, or at least two different parts. Now, if you think about it, when you actually do the downloading part, which is what you guys concentrated on for this last assignment, you're going to write some code that's going to end up blocking for some period of time. And that period of time, of course, is going to be a function of a couple things. It's going to be a function of how big the file is you're trying to download, and it's also going to be a function of things like how slow the network is, or how fast the network is, how loaded your computer is, and so on and so forth. So you have to prepare yourself to avoid the dreaded application not responding exception and dialogue that you'd have. You have to prepare yourself to allow each thread that's downloading to block. Now, again, there are other ways of doing this, but for this particular example, we want to be able to make it possible to have the download thread block. And for that, to be able to have the simplicity of synchronization, we don't want to have to require the code to know a lot about the more complicated interactions with the asynchronous part, because this code should be simple, straightforward, easy to write, easy to understand. We also want to be able to allow these synchronous and asynchronous portions of the software to be able to run efficiently and correctly without making it too hard to program, number one, and number two, without having to require the software to be very inefficient from a scalability point of view. For example, what we're going to end up doing here is we're going to have a user thread, and then we're going to have background threads that are actually going to do the work. Now, think about what you did for your implementation, the way you wrote it. What you did in your implementation for now, for the runnable stuff and for the messages stuff, is every time a user wanted to download something, you went ahead and just kicked off a thread. And that thread was spawned kind of on demand. It's sort of a thread per request model. Now, depending on how you do your user interface, it would take people pushing buttons really fast to cause a problem. But you can imagine a scenario where you would launch lots and lots and lots of threads. You'd have an unbound number of threads being launched. And eventually, those threads start to cost you something in terms of runtime resources on your device. So you might not want to just let unbridled use of threading to be the way that you do things. So what we're going to do to address this is we're going to decompose the software into two layers. Now, sometimes you can think of these as layers. Sometimes you just think of them as two different partitionings of the software solution space. And one part of the software is going to be used to handle the asynchronous part, and the other part is going to be used to handle the synchronous part. So you can see here, for example, in our context of Android, the part that's doing the user interface interactions is going to be listening and waiting for data to show up from various things, like from a looper, or from people doing touch events, or other kinds of interactions you might have through various kinds of interface modalities. And those are asynchronous, and they're asynchronous in the sense that we're not really going to block while they run. They need to run in a way that doesn't block. Non-blocking might be a better term than asynchronous, but the point is that you don't want to block that thread of control. And then we're going to have a bounded number of threads that are going to run in the background. And they're going to be given the actual work to do from the one thread in the user interface part, and then those background threads are going to go ahead and do the processing. And they're going to download the file and then report the results back when they're finished, or any incremental progress that may occur along the way. And to mediate the interaction, the communication between the async part and the sync part, we're going to define a queuing layer that sits in the middle. Now, there's a whole bunch of different ways to do this queuing layer, and we're going to look at a couple of them. We're going to look at a particular way of doing it in the context of the Async Task framework in Android. But be aware, there's lots of other ways to do this as well. And when we talk about the known uses of this pattern, you'll see that there's many other ways to implement this pattern that have different arrangements of queues in different parts of the software. OK, so that's essentially how we're going to structure the solution. In fact, that's essentially how Android structures the solution for some of the things we're going to talk about. So let's talk about this first as a pattern. And I guess what I should point out here, and let me just draw this to draw attention to it. This interaction that we're going to see here is actually the Async Task framework. So that's how Android actually solved this particular problem. So the pattern that is used to document the way in which these different pieces interact with each other is called HalfSync HalfAsync. It's a POSA2 concurrency pattern. And the intent of this pattern is to decouple the asynchronous or async portions of the software from the synchronous or sync portions of the software by introducing two intercommunicating layers, the async part and the sync part. And that is going to allow us to be able to simplify the programming without throwing performance out the window, because we're not going to end up trying to spawn a thread for every piece of work. We're going to spawn a pool of threads and then use a queue to mediate access to that pool of threads. So that's how the pattern works. And we'll talk shortly about lots of different known uses of this pattern as it's applied to lots of things, including Android. And if you take a look here, this is in the POSA2 book. It's also in this paper that you can get at my website. So when would you apply a pattern like this? And as we talk through the applicability, let's kind of relate it back to what's going on in Android, just to make this discussion a bit more concrete. So we want to be able to make performance efficient and scalable, but we also want to make sure that using concurrency simplifies our lives as opposed to complicating them more. We really don't want the application developers to have to know about locking, for example. That should be hidden from them. We don't want to have the application developers know about queuing of messages on synchronized queues. That should be hidden from them. We don't want the application developers to know about spawning threads. That should be hidden from them. So we're trying to hide all the complexities, the lower level accidental complexities of programming concurrency. And we're actually trying to hide some of the inherent complexities. We're trying to hide the scheduling. We're trying to hide the synchronization, maybe even dealing with some deadlock issues here, and so on and so forth. We're trying to make those things as transparent as possible for the developers. They don't have to worry about that kind of stuff. We also apply this pattern where there are different kinds of operations that need to be able to run in different ways in different contexts. So you might have short duration operations that don't run for very long, like adding two numbers together. It might be overkill to do those things concurrently. You're not going to get any benefit. You might as well just go ahead and do them. There's also longer running operations like downloading a file or doing some kind of image processing where things may take longer. So you may want to run those in their own threads of control. There are also issues of blocking versus non-blocking and polling versus waiting and all those kinds of things. So there's different kinds of operations that you may have, and you want to be able to partition where those operations run in a way that's easy to understand and it doesn't get out of control in terms of the complexity. By the way, this particular pattern is very widely applied in operating system kernels, as we'll see, and it's also widely applied in user interface frameworks, and we've been talking about this quite a bit. So what I'm doing now is I'm providing you a more fundamental grounding in the key roles and relationships of the structure of these solutions, but you've already seen a lot of how this stuff applies. So let's talk a bit about how you design things according to this pattern. There's three layers, as you can see here. There's the async service layer, where you're going to do things that don't run for very long. So short-running operations would typically run in the async services layer. And here you're maybe going to get some data, do a little processing on it, and then when you're done with that processing, which is kind of what the user interface thread does, then you go ahead and you offer it, you put it into some kind of queue. And 99 times out of 100, or probably 99.999% of the times out of 100, that queue is a so-called synchronized queue. So all the stuff that we've been talking about with regard to monitor objects and bounded buffers and buffer queues and blocking queues and all that kind of stuff, that's the kind of queue that we're talking about here. So the queue here would be something like the Android message queue or the blocking queue or other kinds of queues like that. And then there'll be some number of threads that wait in a pool in so-called hungry puppy fashion, because they're all waiting to receive work requests from the async part of the world. And they pull the requests out, and then they go ahead and process those requests. And because there are separate threads, they can afford to block independently. And if one of them blocks, not a problem. Somebody else can continue to make progress. OK, so that's essentially the structure of the solution. And hopefully you can kind of see how this maps onto the parts of Android. We'll come back later when we get a little bit further along in the discussion here, and we'll show you how it works in Android. All right, here's sort of a dynamic view of what's happening here, just to give you another flavor of what's happening. So we get the structural part that illustrates the key 3 layers, and now we're going to talk about the dynamics, how they interact with each other. So we start out with data coming in from somewhere. In the case of, say, an operating system kernel, that somewhere is typically a device interrupt from a hardware device. In the case of something like Android, that input is coming in from some device hardware, but it's been abstracted by a bit, and it's coming into your application process probably through the event loop and the event queue that's managed by the looper. We'll look at that when we get to the implementation portion. However it gets in, you finally get the data, and you do a little bit of work on it. In the case, for example, in your programming assignment, you might have done some URL validation. You might have said, is this URL valid or not? A small amount of work. And then you're going to go ahead, at least in the case of the async task, and you're going to say something like execute, or you're going to pass it, or you're going to stick it someplace. And that will end up in queuing the work onto a queue without blocking the caller. And that's really important. You have to make a decision about whether you block the caller or not. If the queue is full, what do you do? Do you fail? Do you block? Do you wait? Do you wait for a period of time? Those are all part of the implementation decisions you would make if you were implementing this pattern. And we'll talk more about that. And then somehow, one of the other threads that's running in the background is going to learn about the existence of the work in the queue. And that's probably because whenever that thread isn't doing anything, it's going to go back and wait for work to show up in the blocking queue. And when work shows up, it'll pull it out of the queue, and it'll go ahead and process it. And that request, since it is running in its own thread of control, can afford to run and block because there are other threads in the pool that are also able to do work. Now, this begs a whole bunch of interesting questions, and when we talk more about the implementation, you'll see that in Java, they do some really, really cool things under the hood as part of the Executor framework and the thread pool Executor framework to handle all this stuff. But in general, you've got a bunch of different degrees of freedom to play with here, and I'll talk about them later. But real quickly, you have to figure out how many threads you want to allocate to be part of this pool, and are they bounded or unbounded? Can you keep spawning threads galore? The more threads you spawn, the less it's a pool, and the more it's just thread per request. And then you also have the concept of the queue. How big is the queue? Is the queue a fixed size? Is it unbounded size? And obviously, there's a trade-off here, because if you're not careful, you can end up allocating way, way, way too much resources, too many resources, and your other things will start to suffer as a result. OK, so keep in mind here that the synchronous services run concurrently, both with respect to each other and also to the asynchronous part. So what that suggests is that the parts in the asynchronous portion and the parts in the synchronous portion should be very, very careful how they interact with each other. For example, they probably should be extremely careful not to try to access shared state directly, because if they do that, they either need to lock it, which could then run into problems, or they'll end up with race conditions. So it's often the case that things in the async layer and things at the sync layer communicate purely by passing messages back and forth. And you'll get a bit more of a flavor of that when we take a look at how the Async Task framework behaves, because that's kind of how it works. It's hidden from you by and large, but that's what it's doing under the hood. OK, so what I've been doing in the past at this point is I've been showing the implementation and applicability. I'm going to defer that discussion, and we're going to cover that next. What I'm going to do now is sort of talk about the consequences of applying this pattern. So here's a couple of things to think about. We've talked about a number of patterns so far, and this is actually a great quiz question. So we've talked about thread-specific storage. We've talked about monitor object. We've talked about active object. And now we're introducing yet another concurrency pattern. So these are a bunch of different patterns. You could argue that thread-specific storage is really more of a synchronization pattern than a concurrency pattern. that's fine. But we've got a bunch of different ways of accessing information in multi-threaded programs. And so it's important to understand the pros and cons of each one. Why would you choose to use one versus another? And this shows up in all kinds of different ways when you start designing your Android code, for example. Because when you start designing your Android code, you have to make a choice. Do I use the handlers and messages idiom, which you did? Do I use the handlers and runnables idiom? Do I use the async task idiom? Which is the right one to use? And of course, there's no one right answer. It all depends largely on what you're trying to do. So we'll talk more about the trade-offs between the different approaches here in a second. But first, let's talk about the consequences of this. So the basic idea is to simplify things without throwing performance out the window. And what I mean by that is we don't want to let the threads grow in an unbounded way. We don't want to make the whole program threaded. We don't want to have to make the GUI thread, for example, the UI thread have to acquire locks to do things that manipulate widgets of various kinds. We want to keep that real simple and efficient. So what we're doing there is we're keeping the sync layer separate from the async layer so that they can be programmed in different ways, each for their own respective idiom. If anybody here is a Monty Python fan, there's a bit in Monty Python about someone's particular idiom. And we'll look at this diagram a little bit later. This is kind of showing how the Async Task framework behaves to these different capabilities. Another key issue here is separation of concerns. So the synchronization policies in each layer are decoupled from each other. In the layer that's the async layer, there is really no need for synchronization as long as you're careful not to access any variables that are going to be manipulated by some other thread. So you just take that problem out of the equation altogether. In the sync layer, again, if you access things, you have to make sure you lock them. And it's possible to lock them because you can block in that layer. So there's different kinds of policies in different layers. And you don't have to have the same behavior used in each place. When we start taking a look at how this pattern gets applied in more unusual environments, things that you are unlikely to ever run across unless you become a systems programmer somehow for operating systems, you'll see that when people program operating system kernels, there's a very different set of locking mechanisms that are used inside the kernel than there are in the user space. And that's because often in the kernel level, you're dealing with things like hardware interrupts, and you have to be much more concerned about interruptions and asynchrony and signals and so on. Whereas in the user level, it's simpler to program from an application perspective. Another thing you get in this model, and you see this when you start playing around with Android, it's very pronounced. You can have this sort of centralization of communication between things. You often funnel stuff through a particular handle or a particular handler with a particular message queue. For example, if you want to get work into the UI thread, there's well-defined ways to do that. You do things like run on UI thread. You pass things in, and that ends up guaranteed to come up through the main event pump inside the UI thread to get the work done. So there's very stylized ways, very centralized ways to talk back and forth between these layers. It's not a big mystery where to go to communicate, although things are often somewhat implicit, which makes it confusing. So those are the good things. There are some downsides, much like with the active object pattern implementation that we talked about last time. Whenever you start to communicate between threads, there's going to be extra overhead that you don't have if you're within one thread. So for example, if you start trying to pass messages between threads, you're going to run into issues of synchronization. You're going to run into issues of dynamic memory allocation and deallocation. You're going to run into issues of context switching. You're going to run into issues of moving data between CPU caches, which is more of a hardware level thing or a bus level thing, but it's still a thing nonetheless. And for people who really care about that kind of stuff, that's crucially important to eking out every last nanosecond of performance. A lot of the application level stuff you might do in Android probably doesn't make that much difference, but if you're not careful, you can make software that runs really slow. So there is overhead here. You just have to be aware of it, and you have to think carefully about what kind of operations you're going to want to run in this model. Don't run long-running operations in the async part. Don't run short-duration operations in the sync part. It's overkill. Another issue that we have here is that we're only using asynchronous I/O for a portion of what we're doing. And that's sort of the lower layer part. So the things that are in the sync layer might or might not actually be benefiting from asynchrony. And later, when we come back and talk in the next section about local inter-process communication, and we start talking about the binder and the AIDL and all these other higher level ways of communicating between processes in Android, you'll see some other cool stuff we're going to add there to be able to do asynchronous interactions between various parts. And it's really cool because now you can make your entire program asynchronous. And that's a whole different pattern altogether. That's more of the so-called proactor pattern that we'll talk about. And again, goes without saying, anytime you start having concurrent things happening, it's more tricky to program and debug. The good news is that if you follow these very stylized frameworks like the Async Task framework, then you can put breakpoints in certain places. You kind of know what's going to happen when. The framework is taking care of all the synchronization for you under the hood, and so on and so forth. And so it makes your life as a programmer much easier because you don't have to worry about this stuff. If you're writing this yourself, you have to be more careful. Next week at some point we'll probably have a couple of people who did particularly interesting solutions to the latest programming assignment present their solutions. And one of the things you'll see is the amount of trouble they went to make sure that the rules for their concurrency framework that they developed are properly followed, checking to see that threads are running on the user interface thread if that's what they're supposed to do, checking to make sure that they're running in the background thread if that's what they're supposed to do. So you'd like that not to have to be the concern of the programmer, the application programmer. You'd want that to be concern of the infrastructure developer, the person writing the Async Task framework, for example, not the person who's using it. OK, so let's talk a little bit about some of the known uses. So this pattern is actually something that I discovered back in 1994-95 time frame when I was a professor at Washington University. And I was teaching an operating systems course. And we were talking about how the operating system kernel worked. And at the same time, I was doing a couple things at the same time. I was teaching an operating systems course. I was developing some software that had to run in an X Windows environment, which had the same quirk that most user interfaces do, where the main thread of control had to be single-threaded. The widgets accessed from the main thread had to be single-threaded. But we had to be able to do long-running downloads of images, so we had to be able to do threads as well. So I had that going on. I was doing some consulting work for some telecommunications companies where they were building switches, telecom switches. And I was also working on an implementation of Corba and playing around with different implementations of Corba. So it was all these different things. And as I was looking at the different stuff I was doing, I started to notice common themes. But the place it really showed up the most was in the operating system. Because if you read literature about operating systems from sort of the 80s and 90s, what you found was that the operating system kernel was developed quite differently from the user level. And if you take a look at this paper down here, you'll get more than you ever wanted to know about operating system kernels. And what's really interesting about this is operating system kernels are typically driven by interrupts from hardware. And so when networking I/O shows up, or when keystrokes arrive, or when data is transferred between different things, reading or writing from a file system or whatnot, those things turn into interrupts. And the way it's programmed historically, this has changed a bit over time, but it's still often the case inside the operating system kernel. An awful lot of the processing that takes place there is done by interrupts. And if anybody's ever programmed interrupt-driven programming, say in an embedded systems class or in an internship, it is really, really nasty because things sort of happen in somewhat of a random way. When the hardware, when the thing occurs, an interrupt happens, and you are not supposed to spend very much time inside your interrupt handler because you can starve out other things from getting responded to, because you typically have to mask interrupts while you're in an interrupt handler. And only interrupts that are even more important than your interrupt, than whatever you're doing, get the chance to run. So typically they program operating systems kernels where there's sort of only one thread and one stack, and everything is driven by interrupts. Well, if you think about it, there's not a heck of a lot you can do in that context. So people invented various hierarchical interrupt schemes. And the long and the short of it is that kernels are driven by interrupts, and it's very, very complicated to program software like that. So that's OK, though, because there's only a handful of people doing kernel programming. And what they do is as soon as they finally get a unit of work that's completely finished, like they assemble different pieces of buffers that come in from a network client, and they put them into one bigger reassembled buffer, they then take that work and they stick it into a queuing layer. And in the operating system context, things for Unix kind of context, that's often called the socket layer. So a socket layer is basically a queuing layer that's used to queue up the data that has come in from hardware devices driven by interrupts in the kernel to be reassembled to be stuck under this queuing layer. Now, hence, from that point onwards, life is happy, because what happens is that application level developers run in processes, and they may have multiple threads, and they can afford to block, and they can do all kinds of other interesting things in those processes. In user space, And they pull the work out of the socket queues, and then they do their thing. And when they're all done, they go ahead and put it back in the queue, and it gets sent out via interrupts. So the point there is that the low-level parts are interrupt-driven. That's the async part. And the higher-level parts are optionally synchronous, because you can afford to block, because you have a process or a thread abstraction or both at your discretion to keep track of all the details for you. So that was pretty cool. And looking at the way that those things work, we realized people broke the system up into these different parts for a reason, to keep the applications shielded from the complexities of asynchrony, but to be able to keep the kernel programmers able to make their software as efficient as possible. Because it doesn't really do you much good to have lots and lots and lots of threads running around in the kernel, because it'll just make things really slow. All right, so that's one example. Great example if you ever end up looking inside things like BSD Unix, which is all open source, or Linux, you'll get a lot out of understanding that pattern. There's also patterns that show up a lot in middleware, things like Corba, where they do much the same thing. You have some kind of layer at the bottom that waits on a lot of different sources of input to get data from sockets. That's the async part or the reactive part. And then those things give the data off into various queues, either one queue or multiple queues, and then there are threads running in those queues to do the processing. That's another example. And then we have the Android Async Task framework. And we'll take a look in more detail in a second excuse me, at the Async Task framework. And you'll see how and why that gets used and what that does to be a win in this context. OK, so those are a bunch of different known uses of the pattern. This is one of my favorite patterns from the POSA 2 book, because it's so powerful, and you see it show up in the most unusual places, as we're about to see. All right, so to summarize, the HalfSync HalfAsync works to simplify your solutions by breaking it up into 3 layers, which makes things easier to debug, evolve, understand. We don't force people to do asynchronous stuff where synchronous stuff makes sense. We don't force people to do synchronous stuff where asynchronous stuff makes sense. Everything is done where it belongs. And the queuing layer makes it possible to avoid directly accessing state. Instead, you can pass it back and forth in a queue. Another cool thing, by the way, that comes from having a queue is you can reprioritize the work. So the order in which things are processed is not the same order in which they have to have been received in the first place. That's not unlike the active object pattern. In fact, one not uncommon way of doing this stuff is actually to put active object pattern on top connected with another pattern called a reactor. We'll probably talk about reactors later when we talk about some of the lower level parts of Java I/O. All right, so that's the end of the overview of the pattern part, with just enough discussion of Android to connect it back to the class. But keep in mind that this pattern really is not at all beholden to Android. We're just using it as an illustration. What I'd like to do now in the rest of the talk is show you how this actually gets implemented in Android. And so we're going to understand how to implement the pattern in general, using Android as examples of how it's implemented. And then we're also going to look and see how you can apply this pattern in Android. And the context for this whole discussion is going to be the Async Task framework. So you'll also, as a side effect, get to learn a little bit more about how Async Task works under the hood, which implements this pattern in a very cool and sophisticated way. It's not for the faint of heart. There's a lot of moving parts inside Async Task, but I'll try to break it down for you so you can make sense out of it. OK, so the first thing you do, if you want to implement this pattern, you've got to figure out what your layers are. You've got to figure out what the async layer is. You've got to figure out what the sync layer is. You have to figure out how you're going to communicate between them. So we're first going to start out by looking at the async layer. So that's the part that's going to be the part where you're doing sort of short duration things. In the context of our examples, that would be the stuff that gets called back by the Android activity framework or the activity widget framework when you click on a button. So you get the view, the on-click event called back that you designated in your manifest file, and you get back the event that occurred, and that's sort of the async part. And for our particular example here, we're going to look at as though someone were going to use the Async Task framework. So what they would typically do is they would bundle up whatever they got in, like a URL or something like that, and then you go ahead and pass that in to the Async Task framework by calling its execute method. And you all remember execute is this template method that does a bunch of things for you. So if you take a look at execute, here's execute from the source code. We'll go and look at this in more detail in a second. But basically what execute does is it turns around and calls execute on executor. And it passes in something called the default executor. And we'll look at that in a second, too. By default, it does things in a sort of a single-threaded manner. But it's easy, very, very easy to do multiple-threaded stuff. And then execute on executor does the following. So it turns around and it does a bunch of stuff, and it calls on pre-execute. So keep in mind, we are in the user interface thread of control at this point. It calls the execute on executor method calls on pre-execute. So that's where that pre-execute hook gets called back. And then it takes the parameters that were passed in here, which are whatever you called execute with, and it sticks them into a data structure. And then it says exec, which is this executor, execute, and it passes in something called a future. And the future is going to be used so that the guy who ends up running this thing in the background later can communicate back to the user interface thread to do things like give progress updates and other kinds of stuff. OK, so that's kind of the first thing. And we'll take a look at the source code here in a second. The next thing you want to be able to do is you want to be able to figure out what stuff's going to run for a long time. So in the context of our particular example, that's going to be the downloading of the file. And the way that happens, of course, in the Async Task framework, if you poke around here for a while, when the constructor of Async Task is first called, it creates something that's called a worker, an M worker of type worker runnable. And this is basically a future. It's a callable. It's a runnable and a callable. It kind of combines a bunch of things together. And it's got this hook method on it called call. And this method is going to be called when you're in the thread of control of the background thread. And as you can see, what it's going to do, this thing gets called in the background thread, and it's going to go ahead and call do in background with the parameters that you passed it. So that's going to go ahead and run in the background. And when that thing is done, it's going to return the result, and that result's going to get posted back to the user interface thread. We're going to look at how all that stuff works in a second. It's really cool. OK, and then the last thing we need is we need some way to be able to interact between the async part, which is kind of that front-end part that does the execute and execute on the executor part, on behalf of the UI thread activity logic, and then get the data over to the background thread and run it in the do in background method. So how are we going to do that? Well, the way we do that, as indicated by the pattern, as foretold by the pattern, like a soothsayer, we're going to do that by having some kind of blocking queue. And as you can see here, what do you know? It's called blocking queue. So if you take a look inside of the thread pool executor, which we'll look at in a second, you'll see that the thread pool executor has a blocking queue. And as long as you give something here that's a subclass of blocking queue, then it will block properly and the right things will happen. So that's how we queue things up. OK, so let's now go take a look and see how all this stuff works. So here's the async task file. Let me see if I can make it a little bit smaller without completely making it so small you can't see it anymore. All right, hopefully you can sort of see that. So one of the nice things about all the Android code is it's all Java docked. So everything you see online is actually included in comments in the class itself. So we can kind of skip down through here and all the things. So here you can see that we have Async Task. Async Task is an abstract class, which means you are obligated to subclass it and fill in some methods. The methods are obviously ones like on pre-execute, on post-execute, and so on. And then it has its generic class, so you have to pass in some parameters. You have to pass in the parameters that get passed to execute, which would be things like passing in a string or a URL. The progress variable, which is used to get called back when you do the on progress update stuff, or the progress update method, and then the result, which is what gets returned from do in background. So take a look here. You can see we've got a couple of things that are used to have a default size of the thread pool. By default, the thread pool will be 5. You'll have 5 things running in the thread pool. The maximum size is going to be 128. They just decided no more threads than that. It's probably not a bad idea. There's this thing called a thread factory, which can be used to make threads and keep track of how many threads we have. There's this thing that's called the The blocking queue, as you can see, the blocking queue here is a linked blocking queue, so it's a queue made out of linked list. And I'm assuming that 10 here probably means the number of elements that can be in the queue before the queue is considered full. We'll see how that figures in a little bit later. Now here's something interesting. This is sort of the workhorse behind the scenes that's doing the heavy lifting for Async Task. The workhorse for Async Task is some kind of executor. And we'll see that there's two of them that are typically there. You are free to define your own executor. If you don't like the two that come out of the box, you can make your own. But the two that come out of the box are thread pool executor and serial executor, which are actually related to each other in an interesting way. So thread pool executor, when you call that, you give it the default number of threads, the maximum number of threads you want, and some other things like the worker queue, the blocking queue, and so on. And that's going to create an object, and that's going to spawn a bunch of threads in the background. And we'll see later how that all works. But then we're also going to make this thing called a serial executor, which is a new serial executor, as you can see down here. There's an internal handler that we use to synchronize communication back to the main thread, the UI thread. That's of course done in the UI thread, so it's owned by the UI thread. We make the default executor be the serial executor. And then here is the serial executor. So by default, an async task is a serial executor. And when its execute method gets called, that turns around and calls this execute method right here. And it's going to end up passing in a runnable. And you can see what we do here is we go ahead and we queue this runnable into the thing called tasks. We have a queue of tasks, which is a deck of runnables. And we stick this thing in here. And we put a runnable in this queue. And then if there's nothing that's currently active, which there won't be when we're first set in here, we call schedule next. And schedule next goes ahead and takes this thing off the queue, and then it executes it in the thread pool executor. But it's only letting one thing at a time be executed in the thread pool executor. And when that guy is done, then what will happen is when the run method is finished, this guy will come back and then schedule the next thing. So we're basically building a linked list of requests, and then they're being executed one at a time. So they're actually not running in parallel. Just one of them is running at a time. That's what the serial executor does. The thread pool executor, when you do it with the multi-threaded version, is even more cool. We'll see that in a second. All right, so let's take a look at a few more things. You can see you can set the executor to something besides the default. Here's the constructor. When you make an async task, when you say async task A equal new async task, here's what happens. It goes ahead and it creates this thing called a worker runnable, which is going to end up being stuck, as we'll see in a second, onto a queue that gets passed to a thread in the thread pool that the executor is running in a background thread. And when it's called back, what this guy does is he goes ahead and runs the do-in background method of this task in the other thread of control. And then we go ahead and make this thing called a future task. And you can see the future task actually holds the worker. So the worker is the guy who's going to do the work in the other thread. The future task then gets created. And this future task, when this guy is done, what he's going to do is he's going to end up getting the result and posting the result back to the main thread of control so that the onPostExecute method gets called in the right context. So keep in mind what these things are. This is what's confusing about this if you're not really a Java expert, is we're making objects that have methods that don't get run until they get called back at the right time. So this guy over here, for example, his call method is going to be called back in the background thread. And when this done method gets called back, he's also going to get called in the background thread. And he's going to post the result so it ends up going back where it needs to go. OK, so there's a bunch of other little helper methods. Here's an interesting one. This is an idiom you see a lot in Android, by the way. So PostResult, we'll see where this gets called. So take a look at PostResult. So here's an example of PostResult. When we ran the background, when we ran do in background in the background thread, when we were finished running in the background thread, it returned a result, which was the bitmap or whatever. And it's going to post that result. So we go here, PostResult takes the result, and it goes ahead and it says, hey, handler, that's owned by the main thread of control, by the UI thread. It says, make me a message, please. And it's going to be the message PostResult message. And I want you to associate with this the result that was just computed in a background thread. And then it's going to go ahead and it's going to take that message. Remember, this message comes out of the handler for the main thread of control, the UI thread. And then it's going to say, message, send yourself to this target. So what it'll do is, under the hood, it'll take the result that was just computed running in the background, and it will stick it on the message queue for the UI thread. And the UI thread will then come along and read that thing out of there and then crack this request open and then do a callback, which will then go ahead and display it in the right place. So if you take a look down here, here's do in background. You can see that that's do in background is an abstract method, which means you have to subclass it. On pre-execute and on post-execute are just virtual methods that are not abstract, so that you can ignore them and they'll still work. Here's on progress update. Here's on canceled, and so on and so forth. Let's see. Trying to think if there's anything else interesting that I should show you here. Here's the execute method. We saw that. Execute says execute on executor. Here's execute on executor. This guy goes ahead and does the on pre-execute because it's in the main thread of control, and then it goes ahead and executes the future and it passes it to the background. We'll look at that in a second to see how all that works. Let's see. Oh, here you go. Publish progress. When you call publish progress, that's how you publish data from the background thread to show up by a call to on progress update in the foreground thread. You can see what it does is it goes ahead and it gets a message from the handler that's running and owned by the main thread of control, and it says, I want to pass the message post progress message, please. And then you can see it just goes ahead and sends that to target, so it sends it right over there. Notice it doesn't even cache the message anywhere. It just changed it together. It says shandler, obtain message, send to target. It's almost like Lisp. It's kind of chaining all this stuff together. Here's the finish method. You can see what finish does. When finish is called, it takes the result and it calls on post execute. So that's obviously how we're going to get the result that was computed in the background to run in the UI thread. Here's the internal handler. This is the guy that actually does the stuff in the background. And you can see that he defines a class. This is another common thing that a lot of people didn't properly handle the memory leak issues, where you have to make sure you have specific classes, not anonymous classes, to deal with memory issues. That's a common problem. Read that link that I sent in my comments to your solution for more information about that. So whenever anybody sends these messages from the background thread to post the progress or post the result, that stuff ends up coming through here in the main thread of control. And what it does is, if it's the message post result, it says go ahead and finish with the result data. If it's message post progress, it says call the on post update with the result data. So those things are how we get data from the background thread to the foreground thread to be called back appropriately on the appropriate hook method that's done on the async task. And then this workable, runnable class is a callable that adds a bit of data. OK, so that's kind of how async task works. Now, the other thing I want to show you here real quick, because it's also quite interesting, is the thread pool executor. And this is the guy that does all the work. So the async task is really just there in order to be able to fulfill the framework obligations of getting do in background running in one thread, and on pre-execute, on post-execute, on progress update, getting those running in the other thread, and then being able to pass futures and worker objects back and forth between the threads using the message mechanisms and the HalfSync HalfAsync pattern. So that's what that thing's doing. The guy that actually does the heavy lifting to run the stuff in the background is the thread pool executor. And if you read this thing, you will realize that they really thought this through very, very thoroughly. My friend and colleague for, gosh, almost 30 years, Doug Lee, great, fantastic computer programmer, researcher, academic. He's the author of this stuff. And it's very, very sophisticated. Basically, it's got lots and lots of different tweaks, little knobs you can turn to do all kinds of different things. He's the author. And so you can either have a fixed number of threads or a fixed number of messages, or an unbounded number and an unbounded number of threads, unbounded number of messages. You can play with all these different parameters. There's a couple different options that they give you to start with. A lot of this stuff is just low-level things. Here's the blocking queue we were talking about before. That's the thing that does the synchronization. not unlike the active object pattern that we talked about. We have some locks in here. We have a hash set of worker threads in a pool, so we can look them up by their ID to find them quickly. But what I really want to show you here was the main method, which is the guy that does the work. There we go. So here's execute. You call execute, you give it something that's ultimately a runnable. And what this thing comes in and it says, is the number of threads in our pool that are currently running, is that less than the size that we're allowed to have? And if the answer is yes, it'll try to add a new worker thread and then give the work to that worker thread. So that's one way it does stuff. If there's already enough threads that are running, it then says, can I go ahead and add this particular command into the queue of commands? Yes or no? And if the answer is yes, then we're fine. If the answer is no, because the queue is full, then in that particular case, we may reject the thing. And then it tries to do some other stuff. If you read the documentation, you'll see all the different logic it tries to do to figure out what's going to work. For our particular case here, we have 5 threads and I think 10 items in the queue. And so as long as we don't exceed those limits, it's going to pre-spawn those 5 threads, and as work comes in, it'll stick it onto the queue via offer. And then if we take a look up here, there's I think it's called take. Yeah, so there's a method called GetTask. And GetTask is going to be called by the background thread in order to get the next chunk of work to do. And it does a whole bunch of different stuff to check its state and context. And then finally, it goes ahead and it tries to get the next item out of the queue using timeouts or not. And once it's got that thing, it's got the runnable that it wants to execute. So if we take a look at GetTask, so you can see the run worker thread. Run worker thread is the actual method that gets run in a thread, and it blocks waiting for there to be work to do. It gets the next task to run. It calls some before execute hooks, and then it goes ahead and says task run. And in our particular case, when you call task run, that ends up calling the call method on this callable thing. And as you can see here, when the worker thread running in the pool by the thread pool executor runs, it's going to go ahead and call run, which is going to call call, and call is going to be related to this callback, and that's going to end up calling do in background from a thread in the thread pool to do its work. And then when it's done, it's going to post the result back to the main thread. So it's almost like watching a game of Pong or a game of tennis. Things are going back and forth through these queues. But the key point is under the hood, it's all working as a result of the HalfSync HalfAsync pattern, where the main thread is sending data to the worker threads through a queue. The worker threads are pulling stuff out of the queue, doing the callbacks to do in background. And when they're done, then they're invoking methods that return the results back to the queue that's owned by the main thread of control. And so that's basically how things are interacting. All right, so that doesn't obviously cover every last thing there is to know about Async Task and thread pool executor, but it at least gives you a feeling for how it works under the hood. So if we were to implement this in the context of our example, we would have a class like download Async Task, kind of like what you guys wrote. We extend Async Task, we fill in string, integer, and bitmap, and then we define a do in background method, and that's the guy that's going to download the thing in the background thread so he can block. We're going to implement the async side of things. So of course, those are going to be the callbacks that we do to invoke things in the first place, like execute, as well as stuff like on pre-execute, which is going to go ahead and display our dialog, and on post-execute, which is going to go ahead and do the operation and dismiss the dialog. So those are examples of the async parts. They run very quickly. They don't block. So we want those running in the main thread. We want the other stuff running in the other thread. And the async task framework makes sure that all things happen in the right place. And then we have the queuing layer, which is what we just looked at a minute ago, where you're going to have this work queue, and the work queue is going to be used to offer and take the messages, which are actually runnables, which are actually futures, which can get called back to do various things as callbacks. So it's lots of patterns all glommed together. This particular set of code has very high pattern density. So in addition to the HalfSync HalfAsync pattern, which is kind of structuring the overall interactions, we've also got futures running around here, and other things that you've seen, factories and so on. And that should be no surprise. Doug Lee has been doing patterns for decades and actually wrote the foreword to our POSA 2 book. So he's very familiar with these patterns. All right, next thing I'm going to do is just give you another view of all this stuff. So I showed you how to implement things. But as you undoubtedly discover, just looking at source code is often not sufficient to make sense out of what the software does. And that's because when you look at source code, you've got to build a mental model in your head of who's calling what and when. And unless you're extremely fluent with these patterns, it's easy to start losing track of what's going on. So how do we deal with this? Well, there's a variety of different means. What I'm going to show you here is a way of using UML notation, in particular some concurrency notation and some notation relating to interaction diagrams, to illustrate the sequence of flow of control here. And probably for the actual MOOC, I will animate all this stuff. I didn't have a chance to do that yet, but here's basically what happens. So the UI thread gets a user request, right? How does that happen? Somebody clicks a button and you fill in a text view or an edit text. You click a button, that shows up by some kind of click handler, right, that you wrote. And you get that, you validate it, and then you call execute. And you give the URL that was part of the data that was entered by the user. So, and let's say, for sake of argument, we set the executor to be the thread pool executor. So execute is called. Execute, as we just saw, turns around and calls on pre-execute. That's the first thing it does. So there's a hook method that gets called back to your code to do anything that's needed to run in the main thread of control. It then turns around, and now keep in mind, this is all in the UI thread right here. All the stuff inside this dashed line is UI thread. It then calls the execute method on the executor, and what that guy does is he sticks this thing into the blocking queue. And I guess, really strictly speaking, I should probably fix this because it's a little bit confusing. Somewhat strictly speaking, the worker threads are really the guys who are running in a separate thread of control. I could probably put this in various places. In some sense, it probably looks more like that, the boundary. So when you call execute, you're calling execute on an object that's sort of half in and half out. It's got a public facade for interacting with it that's called by a thread, and that thing turns around and sticks the request into the blocking queue. And then one of the threads in the background is going to end up calling take to take it out of the queue. And once it takes it out of the queue, it then does this callback method in the background thread. That will then call do in background. That goes and runs over here, and it runs. And then when it's all done, it will go ahead and post the result. That ends up coming back over here, and this guy gets to run in the other thread of control. So the executor threads in the thread pool do all that work in the background. And under the hood, the blocking queue is what's really doing the synchronization of interactions between the HalfSync and the HalfAsync layer. If there's flow control that occurs at all here, if you were to happen to block in the one thread of control or in a background thread that's doing a download, not a problem. Nobody else is affected. Everything works just fine. OK. So to kind of wrap things up from an Android-centric perspective of this pattern, you can kind of see here, this is the pattern, but now we've replaced the generic parts with specific things from the Android toolkit. So we've got our external event source is really coming at us from the UI thread looper that we looked at before. Our activity is kind of the part that's the async part, because we're not blocking in there for any length of time, because we'll get the ANR exception. And then we're offering stuff into the blocking queue, which is part of the Async Task framework. And then these background threads are pulling stuff off the queue, processing it, and then they're eventually passing data back to the UI thread through that internal handler mechanism that's used to synchronize messages between the background threads and the foreground threads. So this is actually, as I said, well, I'll get to that in a second. So this encapsulates background thread processing, decouples it from the UI thread. You can also report progress. The HalfSync, the Async Task framework is a very sophisticated implementation of the HalfSync HalfAsync pattern. And it's sophisticated because unlike many instances of this pattern where data just flows from the bottom to the top, we have data flowing from the bottom to the top or from one side to the other, it depends how you look at it. And then there's also stuff coming back the other way. So we're not just having one-way communication. We're talking from the activity to the background thread, and then from the background thread to the foreground thread, and sometimes, as is the case with the post-progress stuff, that happens multiple times. You keep calling back and forth for the duration of the call. So there's multiple points of interaction between background and foreground threads, or UI threads. Okay, any questions about that particular pattern or that framework? So now hopefully you have a much better understanding of a couple things. You hopefully know a bit more about the Async Task framework and how it works under the hood. You might see how it's implemented as a pattern, which helps it easier to understand the implementation. And probably the most important thing you learn is that nobody in their right mind would want to implement Async Task if they could use it from what's already in Android. So it's a great story about how patterns and frameworks collaborate to make your life easier if your needs match what it does.